So now in this video I want to reuse a setup I came with. So this mini oscilloscope has alligator clips that come out of that cable there, and it is powered by, in this case, a 9-volt power supply. You want to keep it close to 9 volts, and the power supply came with the meter, and the meter came assembled. Some of these need to be assembled, and so in any case they're about the same price, I think, at least from what I've seen. So in any case, we looked at this setup in the last video, so I'm just going to kind of quickly refresh, and the breadboard is trying to reject the trim pot, which it does. The leads don't fit perfectly, and I've been having problems with the pins wearing out the board. But in any case, if you look at the line there, I raised the voltage of the trim pot. Each one of these squares is 5 volts going up. You can see 5 volts there, and then it's 1 second going across. So you should be able to tell that it took me a fraction of a second to turn this, and I didn't quite land all the way before I stopped. You can see that reflected there. So there you go. So we have the sudden change. So this video is going to focus on the capacitor. So as you can see, based on where I have the trim pot set at any time, it's wired as a voltage divider. We're getting 0 volts down here and 18 volts up there, and halfway point is going to be 9 volts. And so what we're going to do, we're going to take this capacitor. So this is a 1000 microfarad capacitor, the same as a millifarad capacitor. It can be charged up to 35 volts, so we're nowhere near its maximum voltage. And we have a little space here because I'm going to add a resistor, and we're going to measure the voltage of the capacitor. We can go right to the capacitor, and it looks like I discharged it before I made the video. And we're going to take a 1 kilo ohm resistor. So that's going to go from the capacitor there to the trim pot, because the trim pot goes rail to rail. It has 10,000 ohms of resistance, but if I go all the way to one side or the other, then the wiper is touching that rail directly, and so it would instantly charge or discharge the capacitor. As you can see, we already have a voltage difference between the trim pot and the capacitor, so the line moved. So in any case, let's shoot down to 0 volts first, and you can see we have a curve now. So the voltage of the capacitor changed rapidly at first, but now we have a resistance here. As the capacitor gets closer to 0 volts, then there's less of a voltage difference between the positive side of the capacitor and the negative rail going through the resistor. There's less voltage difference. Negative rail goes back. There's a jumper there that goes to the negative rail. So that's a direct connection. The only thing limiting current is the resistor. And as current goes down, the change of voltage goes down. So now we're going to rapidly put this up to the 18 volts, as we saw earlier. That took a fraction of a second. There we go. That was about the same time. You can see that it rapidly went up. And what we're going to do is, after it goes a little bit, hit that button, it will pause. So that landed pretty much spot on where I wanted it. So we can see here, this is what they're talking about when you hear RC time constant. So we had the capacitor charged to 0 volts. We shot the trim pot to 18 volts, and which is about there, because each square working your way up is 5 volts. So 5, 10, 15, you can see 15 there, and then about 3 more volts right there. And it shot up really fast. So you can see that within about a second, which is the RC time constant for a 1000 microfarad capacitor, you multiply that by the resistance, so that's 0.001 1 millifarad, same as 1000 microfarad, times 1000. So 1000 times 1000ths is 1. So after 1 second, that 1 gives us the number of seconds for a time constant. We get about 63% of the final voltage. So we went from 0 to 18, and then the next second we're getting about 63% of what is left. That's our final destination, and again about 63%. So as you can see, it's going slower and slower, and after about 5 time constant, so 1, 2, 3, 4, 5, so right to the center of the screen, that's usually when you consider it completely charged. So it's gonna still kind of trickle its way up, but as you can see, it looks like we pretty much flatlined there. And because you never mathematically completely charged, you just keep getting about 63% more charged for each time constant. And so in any case, that's for charging. And of course we can click OK now, and I don't know why that dropped down there. Oh no, I don't have a clue why that dropped down there. So I don't know what's popping in the background, so sorry about that. So let's go take the 18 volts and let's drop it down to 0 volts real quick, and you can see we have the same thing. It rapidly discharged really quick, and then it slowed way down. So there we go. So just before we got to the line, you can see about 1 time constant. Again, the time constant is the same because we're using the same capacitance and the same resistance. We're just going from 18 volts to 0 volts instead of 0 volts to 18 volts. But you can see the same thing. The voltage changed rapidly and quick because we had 18 volts at the positive side of the capacitor and 0 volts over here, which goes to the negative rail, that side of the capacitor. So we had a large voltage, 18 volts across the 1 kilo ohm resistor. As the voltage went down, less current can pass, and there's less voltage change. So a 1000 millifarad capacitor, same thing as a 100 or 1000 microfarad capacitor, is the same as a 1 millifarad capacitor, I should say it that way, with 1 milliamp of current flowing through it, is going to change 1 volt. But it was higher, the current was higher when the capacitor had a higher difference than the trim pot. So the voltage changes faster because there's more current, but as the voltage evens out between the capacitor, and in this case the other side of the capacitor, it was discharging across the resistor, the voltage across the resistor drops, and it lets less current go through. And the less current that is changing plates of the capacitor, the slower the voltage change. So hopefully that all made sense. That's basic capacitor stuff, RC time constant, but it's nice to have an oscilloscope like this to show those measurements in real time. You'll see a lot of waveforms when you're reading about them and stuff, and so if those waveforms were kind of confusing, hopefully this helped out. But that's the main thing to know about these capacitors. They're really not intended for energy storage. If you want to power something for a while, you're going to need supercapacitors, and you're probably better off with batteries anyways, unless you need a short burst of very high current. Then supercapacitors can be very nice. But usually when you power stuff, you're powering with a battery. These are energy storage, but the storage is more in relationship to the amount of current they need to gain or lose to change voltage over time. And so mostly you'll be using the RC time constant or using them to smooth out. As you can see, it held a voltage for a bit. We tried to give 0 volts, but it took time for it to go down. So if you have rapidly changing voltages, it dips down suddenly for a short period of time or something, a capacitor can provide backup power to make that dip much less noticeable. And if you got enough capacitance, it will just hold it steady, as long as you can provide the current that that dip would otherwise take away from something else you don't want it to take it away from. So, in any case, please subscribe to my channel if you haven't already. Please click the like button, and I put links in the description down below to my Amazon page and other stuff. And some purchases I get financial compensation after people have clicked my link and whatnot, so that will help me out. So if you want to help out the channel, you can do that. I also have a Patreon, which I put in the link. So any help is great, and whatever you want to do, but mostly I'd like people to watch my videos, click like, and just have enough viewers where that's all I need, are the viewers of YouTube videos. So thanks for watching. I'll see you in the next video.